And he'd tell them, yeah, well, take your tape measure, measure from here to about this point, and he'd measure, give him a number, and he said, measure from here to there, he'd give him a number, and he'd calculate and say, okay, you need to cut your sheet metal this far, you need to cut the sheet this far, that's all he did. But, you know, who was the most respected member of that team? It was him. Because the other 5 people were just amazed he could do this. They come up with numbers that worked. There's a lesson for all of us there. Yeah, how many people are accountants or bookkeepers? And the only thing an accountant does is just say, I keep track of the amount of pennies you make and the amount of pennies you spend. It really is just that. Yeah, how many people, you know, sit there and think, wow, what a job. In fact, around here, you probably know a bunch of multi-millionaire accountants. They ride horses around here, such on and down. A lot of them run accounting firms in New York, where literally it's just count for, okay, $5 in, how'd you spend it? Math, primary purpose is not to employ math teachers, even though they may believe that. It's really a tool, just like in your toolbox. You have hammers, screwdrivers, wrenches, pliers. It's a tool to be used. It's used to describe something in another language. It's really almost a language. You want to describe the length of an event from here to here. I want to describe that length. How would you describe that length? Let's see the choices. A. Something. B. Yay long. C. "14 inches. D. Don't know. Ask somebody. Which answer seems to be the most useful?
That's what yay long.
Hmm?
That's what yay long. You gotta throw up the hands though, so like yay long.
Well, I don't have to, that works here. But imagine that.
14 inches.
Yeah, that's
Yay
yay
long.
long. Yeah.
Almost touchdown, field goal,
Yeah.
something like that. You know, yay long, I really can't cut to and make an accurate cut. I couldn't make an estimate, say, if someone said yay long, something like that on my head, a 3-foot length section of something, and they could trim it down. So I mean, it's not totally useless. Something is probably useless. Don't know, ask somebody else. Answers A and B would probably be the same thing. Ask somebody else. Or if you just pull up a ruler yourself or a tape measure, you go, it's 14 inches. So that's kind of the same thing in math. Well, the thing in calibration, I'm gonna use math to put things in perspective, so what's going on. So that's where we're heading with this talk about sensitivity, proportional gains, proportional bands. You know, from a technician standpoint is, why would you care? You know, it's like designing a rocket ship. If you're writing an airplane, well, if you're writing an airplane, you really care about the design of the airplane? Not beyond reliability, and reliability is really a hand-waving numbers. You really don't know what the reliability number is in the plane you're writing. But you don't worry about how you sit in it, how comfortable you are, how rough the ride is, how on time it is, that sort of stuff, and does your luggage make it with you? So there are certain things you care about. Now, if you're a baggage loader, you worry about the baggage loading up the ramp, where the doors are, how hard it is to get luggage in there. Probably as a passenger would too, because you look out the window and you see your luggage falling from there to there on the ground there, going plop, 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 and opening up, and half the stuff's going down the runway. And all of us travel enough there, eventually see that sight. You know, it's in there. Well, for technicians, it's in calibration and checking things. You notice I said checking things. But now, in the lab, when you do labs, there's a couple in general. This is in general, every lab. Ultimately, what are the things you should be getting out of here after somewhere around 2 to 20 years here? The record for a degree here is 18 years, as far as I know, as far as anybody I've met. What are the things that we'd hope to get out of the lab environment? Measurement, tools, and we'll call it general. Ability to handle tools, ability to do measurements, understand what measurements are, what you have to measure, how to measure. So there's a what, why, how, and more importantly, really the what and the how. A lot of why is your boss says, measure this. That's enough of a reason. So the what and the how are the how are the important ones. Why is nice for context, and sometimes why lets you know what and how. So it's not totally useless. I mean, if you're checking why as far as measuring power, just say you have power or not power, then you're not typically worried at 120 volts, worry about the 10th of a volt or the 10th of an amp. If you're on the other hand, you're doing a 420 milliamp current loop, you're worried about that 0.001 milliamp. Whereas before a measured motor current, you throw away the 10th of an amp. And yet, current loop, you're worried about 1/1000th of that. Or 100th. So why does matter a little bit. Tools in general. Definitely this is a how. How to use general tools, what they are. And then you want something about applications. What to do, how to do it. And again, I'm talking about generalities. Like if I tell you to go out and set up a motor start stop circuit, what does that involve? Presumably you have a motor. Presumably you have a motor control panel. Or if you don't have one, you're going to get it. And some switches, probably, and some, possibly at least a motor contactor, if not more control relays, overload relays, that sort of stuff. How to do it, what are the steps in assembly, in general. Not the specific case necessarily, because it may be, you go on a new line and say, okay, you need a motor control center to turn on this and this motor, wire it up. They may have built the center already, but it's up to you to wire it. Now I'm thinking of a civic student we had, graduated, and 2 months later, that was his job. He gave a panel that was about this high off the ground and said, wire it. He did, successfully. Nice job. Sent me pictures of it. That's how I know he did it. That's actually good work. But that's something that's you'd expect to do. And as I said, he was a 2-month graduate from here, so you kind of get a time frame for when you might see something like this. The tools in general. What kind of tools? As a minimum.
Like a multimeter?
Well, multimeter, right? So you get your DMM. You also have, presumably, wrenches. Cutters, usually wire cutters at least. Screwdrivers. There's a lot of hand tools here. You also may have something like a chain vise for holding pipe. If you're doing some pipe threader, if that's involved. That may not be a general tool that you carry with you all the time, but you probably have a toolbox. You imagine you have a toolbox here and you probably have in it screwdrivers, wrenches, probably pliers as a general thing. When the wrench doesn't quite do. Now you may have pipe wrenches, you may have, I doubt if you have chisels because most of your work's around metal. That's woodworking stuff. So an industrial standpoint, most things turn about into metal, so definitely drills too, and drill bits, decent drill bits. Not Craftsman wood cutting crap. Hammer, most likely. You got an idea, a selection of hand tools and a digital multimeter, and probably wire cutter stripper for any electrical work, because even the mechanical people will have to do some electrical work. Not a great amount, but it's still the case of running this wire here, and many times it's a mechanical person doing it because they happen to be the person there. Measurement. Length, not necessarily weight necessarily, could be if they're doing rigging, but certainly measurement of lengths. If you're gonna do any mechanical layout of pipe, you have to know, gee, this is 5 foot long, how much space do I have? Or I need to run a pipe from that wall to that wall, with a bend in it, or I might have a pole here to go around. So there's some mathematical involvement in that, as well as being able to take measurements. The measurement implies some math, because sometimes you have to add numbers together. Like we're running a pipe from that corner to this corner. Is there any math involved at all?
Yes.
Most likely, because the first time you have a bend, you have math. Because the distance from that corner to this corner, there's a straight line measurement, but that's useless because you're probably not gonna run a pipe down the middle of this room. You run it around that wall, bend that wall. And so, as simple as that is, you have to account for the fact you go around that wall, around this wall, and an allowance for the bend. And also allowance for wasted on each end, and perhaps a little bend down to a box, because the boxes may not line up perfectly where your run would be, that sort of thing. So there's some math involved. Tools and application. These are general things. They really haven't named much that's, they sit there and say, but it's that class, or it's that, or this. It all kind of blends in together. And one of the things you find as you get more experience in maintenance and technician work, that you see all this little stuff we call this class, that class, just kind of blends in together. Well, it's kind of like hydraulics pneumatics class. You have a class of that, you have a class of motor control, but in the end, you want to deal with electro-pneumatic control. And that's really a blend of 145 and 131. Blended together. It's all one thing. Even the equations for hydraulic flow and pneumatic flow really are the same as electronic ones. We just have different names and different variable names, but they're exact same equations. You still have resistance to flow or resistance to current. You still have pressure versus voltage. You still have gallons per minute flow versus amps. Oh, that's the same numbers. In any case, we go through a little situation and show where some of these numbers come from and what we do with them, where they, and what sort of things we come up with. Now here, a very important thing is following the units of measure. Now, when you're adding inches and inches and inches, like 12 inches plus 6 inches, and you can sit there and say 18, and somebody would probably understand from context you meant 18 inches. But when you're talking about flow in gallons per minute and signal in terms of milliamps and possibly a pressure on the pressure sensor, PSI, that's 3 different units of measure. And particularly when you're talking about transfer functions, which is really what you calibrate, which is it? How many of us screw up reciprocals? Think back to your days, and when was the last time you do parallel resistors? Anybody remember when you did parallel resistors last? How much trouble were reciprocals? There'll be some people that say none. Some people here that say it was, a light street, never have to do one again. Somewhere in between, but you have to pay attention to it. And that's what gets the point is, many times, if you had carried the unit of measure through, you'd see if you're one short of the number of reciprocals you have to take versus one too many, versus the correct number. Now, anybody that's seen me, write down, say, a 300 ohm resistor in parallel with a 300 ohm resistor, a 600 ohm resistor, let's include resistance, pick a number from electronic devices, class the last couple of people have been helping me out with the lab. I'll call this R1, R2. And RP. And for this to be equivalent to the outside world means if I hook up this wonderful 120 volt supply to it, what's the current that it would see? And that current should be the same value. Just like this is the same value as that. And that only occurs when that's the same resistance as that. That's really what we get to when we talk about equivalent resistance. It's not internally equivalent, because there's two different current paths, there's one current path here. That can't be equivalent. But for the red, it looks the same. It's kind of like job assignments. We had a whole bunch of job assignments. You're all junior technicians, technician 1. And I have a job to do by 3 technician 1s for 40 hours each. 3-man weeks. I have a schedule that says technician 1, 120 hours. That's what shows up in the Gantt chart, PERT chart. Gantt chart is what I like to use personally. Only on a project. It doesn't say a key versus Denny versus Blake. Because presumably, the 3 of you can do roughly about the same job. Reality, maybe not. But reality is, you'd be surprised how close you would be in a company as far as, because the bad John Doe gets filtered out somehow. The really great Jane Smith got promoted, becomes a technician 2. So technicians 1 are all really about the same capability. In fact, surprisingly close. Most of us think we're better than average workers. In reality, we're almost all average workers. It's kind of like engineers. I remember working around Greg Barton. Greg Barton was kind of a lackadaisical type, walking down the hallway, and that's all people would see him, other than his office. Well, I get the impression I do twice the work with Greg. I asked Greg what he was up to and that sort of stuff. He gave me a long list of things he was doing, and at the end of it, I was sitting there thinking, this is the observability law. I might see Greg 25% of his workday. I'll see 100% of my workday. So I'm thinking I'm doing 4 times the work he is. In reality, I'm not. It's just not paying much attention to him. In fact, the more work I do, the less I pay attention to him. In respect, in reality, he's doing more work than I am. He's probably saying the same thing. That goof off Nolan is screwing the pooch. Because he only sees maybe 10% of what I do. He's paying attention to his work. There's that observation. But a technician 1 is going to be, 120 hours. This goes in the schedule. That's really what this gets down to. Said whether this was Blake and a key and Denny or some other thing like that, immaterial. It's just a generic approach to the red. And so how to solve this? What's the equation for solving this?
I over VR.
Forgetting RP. What's the equation?
Oh.
You have the reciprocals of the 2 resistors, and you take the reciprocal of that.
Yep.
What adds in parallel?
Current.
Current adds in parallel. When you do a layout for circuit breakers, and you have loads on the circuit breaker, whether you do it in your house or whatever, I'll take the house case. You put down a bunch of receptacles. Receptacles are 180 watts per duplex strap. If a quadplex, that's 2 straps. So 1 or 2 receptacles per strap. NEC says allow 180 watts if you don't know what's plugged into it. And so 180 watts, 120 volts, use nominal voltage, is 1.5 amps. So if I have 10 of them, and I put them on a circuit breaker, what's the current drawn on the circuit breaker? 1.5 amps per strap, 10 straps. What's the current?
15.
Allow for 15 amps. You notice you added the currents. How do we hook up those receptacles?
Parallel.
In parallel. You hook loads up in parallel, current adds. That's how you calculate circuit breakers. So you do everything now. So we add the currents. By Ohm's law, what's the equation for current in terms of voltage and resistance?
Voltage divided by resistance.
Okay, that's by Ohm's law. You accept that. So that's my equation for this. The current through resistor RP will equal the current through R1 plus the current through R2. Make sense? Now, I'm going to put this in terms of Ohm's law. The current through RP will be the voltage across RP divided by the resistance of RP. The current through R1 is the voltage across R1 divided by the resistance of R1 plus the voltage across R2 divided by the resistance of R2. Now, what do I know about those voltages?
They're the same.
Same
They're
thing.
all the same because in parallel, same voltage. So I can assume this is 1 volt, or I can just flat out just divide the whole equation through by a volt. And that translates into 1 over RB equals 1 over R1 plus 1 over R2. And that's the equation for parallel resistance. That's why it's reciprocal. You're really adding the currents. Take the Wildcats, because I did mention what the voltage was initially here. I did say 120, but it could be any voltage. There's still the same equivalent resistance. So that's our equation. And that's a function of keeping track of the reciprocals. On a calculator, we know this would be enter 300 reciprocal key plus 600 reciprocal key equals reciprocal key, and you get an answer. Use the scientific calculator, and the order of precedence takes over. Multiplication and division over addition, subtraction, and its functions like trig functions, exponents, which really reciprocal key is x to the minus 1. Take precedence over multiplication and division. So that's why you said enter a number, reciprocal, plus enter a number, reciprocal. That last reciprocal is only of the number after the plus sign. You'll add the two reciprocals that way. Has to be a scientific calculator. Standard calculators don't have order of precedence, they just go left to right. But they won't have a reciprocal key either. Gotta be a little clever using those. But scientific calculators, which almost everybody's smartphone has some sort of, that's what they do. And the number you would come up with here would be 200 ohms. So this, 0.4 amps, this, 0.2 amps. So now it's going to be 0.6 amps. Very straightforward. Notice in the lab, when people were setting resistor values, they told you to set 200 ohms in that resistor module. I always said add the currents. Because you have a 300 ohm resistor, 600 ohm resistor, 1200 ohm resistor, you apply 120 volts across them, you get 0.4, 0.2, 0.1 amp. And if you want something like 200 ohms, simple, divide 120 volts by 200 ohms, you need 0.6 amps. Flick switches until add it up to 0.6. That's really all you're doing here is 0.4 plus 0.2 equals 0.6. It's the same thing. A little different wording. Now, realistically, the only thing experience, obviously I have a lot of experiences, really adds, is I have about 3 or 4 ways of stating the same thing. That's the only difference here. And you all have done this, you're capable of doing it, you've done it successfully, continue to do it successfully. And And as you work with it more, you'll sink in more what you're doing, which is just adding currents. Or other things you do, the same sort of thing. It's kind of like filing down key seats or anything else. You look for certain smoothness, you're done. And you learn those tolerances and that sort of stuff. But still to get back into control. We're going to take half the problem full problem is going to be pump, let's do it this way. Get my act together here eventually. Actually, we'll take this. On the instrumentation side, how many different instruments are there here?
Four.
Four. And you identify four because of what? Tags. I'll throw another one in here. It's basically a hand valve. It's not really, they put one for pump too, but realistically, it's four instruments. They are, the top one's a computer, right?
Yes.
FY is what? It's not an indicator, it'd be FI, it's FY. Tricky question, but you got a number of people on in a lap 3 assignment here. Notice it converts, it's tied to a diaphragm valve. So diaphragm valve, which way is this signal going? Which way do these signals go?
Towards the valve.
They're going from the controller to the valve. Electrical, pneumatic, diaphragm, pneumatic is what's wanted, so it's an IP converter.
Yes.
So yeah, Y just means general instrument, which could be redefined as something else. In this particular case, it's clearly an IP converter. So that's an IP converter. What's FT? Okay, it's specifically doing what? It's a flow meter that's transmitting the information back to the controller. There's no indication it displays anything. There's no gauge for operators, just simply it's electrical signal sent back. And of course, LT then is a level transmitter, doesn't say what type. You can presume pressure, for instance. That's a presumption. We know at least it's a level type, probably pressure. Going back, and HV, of course, is a hand valve adjustment for draining the tank, set to whatever. Inspired, of course, by your lab. The stand looks a lot like this. Pump's free running. Valve to shut it off and control. There's other hand valves involved, rotometers, etc. This is a basic loop. I want to keep it very simple type of thing. Now, there's various signals here. The important signals as far as control are which ones? You start electrical, not all electrical, but the paths we're concerned with are basically LT2 controller. We have controller 2 IP converter. I could have made this a valve of some sort. It's a flow valve. So we'll throw a tag in for that. IP converter to flow valve. Lastly, LT. Actually, I have LT all the way to there. So I have this accounted for, this, and flow. What seems to be the primary loop here? A flow or level?
Level flow.
Level is the primary loop. There is a flow loop involved as well, but it's subservient to the level. It's really we're adjusting flow to get a level, and not adjusting level to get a flow. The flow loop is pretty tight. We adjust the valve, meter comes back to controller, that's your entire loop for flow. Your level flow is the big one. It takes this is the control for it, but this is our process and measured variable going back. It's a bigger loop. And so level loop really contains almost entirely the flow loop. Your big loop is a level loop. That's why the controller is labeled an L rather than an F, because it's really controlling both F and L. So it's like, okay, which process variable should we list in there in the tag? Now you know. The main process variable is what gets listed when it gets multiple. Where are all these things mounted? All that instrumentation.
In the field.
Like right on the line. Even the computer is right there on the line. Nothing's in a separate control room or a separate building or separate auxiliary panels. There are no auxiliary panels as demonstrated here. Is anything shared?
No.
These are all individual devices. They're their own devices. There is an indicator on here, which I expect on a computer. So some way for an operator to interface with. So it's almost all of your computers are going to have some point where an operator can interface and set something. And it is possible to have operators completely out of the picture as far as setting things. They still have the emergency stop button, they still have a push button for start. So beyond that, it's nice to have, but almost always you're going to have some sort of indicator for an operator to see. Otherwise, why are they standing around? So you have 4 things to describe here. Each of these are going to involve, each link will really comprise a couple things. There's some sort of a transfer, there's some sort of an input range. There's some sort of output range. There's a transfer function. That describes each of those links. Now, each sensor, each input and output to the system, which means sensors and valves, are also going to have something that doesn't go back to the controller, like a physical quantity. So if we pick on any one thing, I'm going to pick on level transmitter, for instance. You have a level transmitter function. What's the general input into his level transmitter? Tank level. What's the output? Well, we know the output goes to the computer. It's electrical. So it's going to be something like a current loop. I'm going to say 4 milliamp, 20 milliamp current loop. I'm going to assume that for everything for electrical, because that's, I can make it up, that's actually what we use out there. So do we have everything we need to set an input range, an output range, and a transfer function here?
No.
Include the diagram? We kind of do, and it's a qualified yes. Assuming we want to go to 10 inches, from 0 inches, then yes, we would. Now, if we said we don't ever want to go beyond 5 inches, maybe not. Maybe we want to modify the input range. Most likely we don't want to do 20 inches if the tank's only 10 inches high, because that'd be overflow. You never hit it. So I mean, there is a limit to the input range that's going to be top of the tank. Why top of the tank? It's as far as we go in a tank. Put more water in it, what happens to it? It flows out of the tank. So we don't measure anything higher than the top of the tank. So we were way back proportional band, so 2 days ago. Is a limit on a range. So what's our proportional band limit on a tank? Well, it's going to be 0 inches to 10 inches. Why? Can we have a negative tank level?
No.
No, once it's drained to 0, it's drained to 0, it's dry. It can't be extra dry. It's just dry. So 0 is the bottom. What's the top limit? In this case, 10 inches, because anything above that gets flowed out of the tank. So some proportional bands are set for you by a physical limitation. That's all it can do. Possibly even on signals like 4 milliamp to 20 milliamp, not all receivers can adapt and say, I can handle 2 milliamp, I can handle 24 milliamp. They maybe can, maybe can't, but usually in most communication systems, we arbitrarily set on 4 milliamp to 20 milliamp bounds, saying if it's less than 4 milliamps or greater than 20 milliamps, we make that an illegal signal. So we have a proportional band limit on current loop. .00 milliamp to, I'll put 000 to 20.000 milliamp. Because I wanna be able to recognize illegal signals, like if I have zero current, I wanna be able to detect zero current as a broken cable. Open circuit. So from a practical standpoint, I don't wanna have my proportional band as low as 0. I want it to be higher than that, so I can detect broken cables. I don't necessarily want to be higher than 20 milliamps, because that appears something else is wrong here to the driver perhaps. So notice here, proportional bands. First thing you start reading proportional bands, you say, well, gee, the wider the better. Why can't I cover the world? And, you know, theoretically, hypothetically, certainly, and even theoretically, if you have no limitations to your abilities to handle such things, there is no reason to limit anything. But we do have practical limits here on proportional band. One of them here is physical. I don't want to necessarily measure beyond 10 inches, because beyond 10 inches, I'm in trouble. I don't want to measure less than 0 inches. Just can't get there, not even erroneously. So if I did get a signal indicate less than 0 inches, I know there's a problem. If we get something more than 10 inches, it's time to man the boats. We're swimming for the shore. So there's a proportional band limit that no matter how wide I make my proportional band fit my equations fit that, I'm limited to this anyway. I'm never going to go outside the 0 to 10 inch range. So I have a proportional band limit that's fixed. It cannot be larger than that. Proportional band limit on current loop, it's 420 milliamp, because I want to say anything outside there is an alarm. Now, notice in your Amatrol text, a lot of writing even on Google, such on like that, they'll mention proportional band is equal to 1 over Kp, Kb being your proportional gain. But realistically, that's almost better to say less than or equal to allow for the fact we may be limited by proportional band by this sort of thing. So it may not be, you know, equal to the reciprocal gain. In other words, we may want to have more gain than we need, but unfortunately we can't use it for gaining wide bandwidth. So our take level, 0 inches to 10 inches. Now we set an input range, which effectively is our proportional band, because that's what we want to transmit. Now our actual proportional band may not be that, because we may hit limits on the output due to our transfer function. We'll show that a little later on. We do have a fixed limit on this. I'm going to use that fixed limit. Our computer is going to be 4 milliamps to 20 milliamps. So what is our transfer function? We have an input range. We have an output range. What's a transfer function look like? Of course, I think half of you are sitting saying, what's a transfer function? How many people think, what's a transfer function? And that's reasonable. You've probably never heard that from your math teacher. It just simply says it's an operation or function here. I call it a transfer function because it's going to take this input, transfer it into a usable output by the computer. So it's not only going to be a math function like y equals mx plus b, but it's going to be a useful transfer function because it's actually going to give us the numbers we need. We're going to operate on in the system, and we're going to have another one for that until ultimately a complete loop that will actually control the take level. We're actually going to apply that math that's covered in high school algebra, math 101, 102. As Billy just saying, it exists. The transfer function equals output divided by input. Looks an awful lot like gain. It is a type of gain. The reason why I just don't call it gain is because gain is always what we call unitless. Inches per inch, feet per feet, pounds per pound. How we multiply force. You know, if you have a lever arm, for instance, fulcrum That distance is 1 foot. This distance is 3 feet. If I were to drop 2 pounds here, how much force is generated here?
Six foot pounds, 6 inch pounds.
Force. 6 pounds.
Yeah.
You're right about the foot pounds. That's really the equation that you're going to use here. Input foot pounds equals output foot pounds, assuming 100% efficiency. 2 pounds, 3 feet, 6 pounds, 1 foot. This multiplies the force, doesn't it? That's how I sit there with a scissor jack. I'm jacking up my car to replace my rear wheel. You know, it's a 2-ton truck. The back half of it's probably at least a ton. Actually, maybe half a ton at most. Most of it's in the front. But still, I'm not lifting a half ton off the ground. I know people are good to it. I'm not one of them. Partially laziness, partially my knees are shot and elbows are shot. I'm just not losing. So how do I jack it up? I use a jack because it gives me mechanical advantage. Basically, it's called gain. What's the mechanical advantage of this system in terms of force? It's 3.
3.
Right? Mechanical advantage equals 3. 3 times. That's a gain. Notice there's no unit there. Because it's pounds in, pounds out. Output, 6 pounds. Input, 2 pounds. The pounds divides out, I'm left over 6/2, which equals 3. So my gain is 3. Mathematically speaking, it's that. There's no unit involved. Now, in a system, I have a force N, and I generate a torque out. My output now is torque. My input is force, and that's my transfer function. So when I drop 2 pounds there, how much torque am I going to generate? Force, I generated 6 pounds. Torque, how much torque do I generate in this particular system? So if I drop 2 pounds here, 3 feet, how much torque do I generate?
6 foot pounds.
6 foot-pounds. 2 pounds times 3 feet, that's 6 pounds of torque here I'm applying. If I get 100% efficiency, I get 6 foot-pounds out. So I have 6 foot-pounds divided by 2 pounds. So my transfer function or gain here is 3 feet. Sounds weird, doesn't it? But saying whatever my input force is, I multiply by 3 feet to get my output torque. Let's try this out. What if I drop here 4 ounces? What torque do I get out?
Well,
12
I get 12
foot pounds.
foot ounces.
Oh, foot ounces. Yeah.
How do I get that? 4 ounces times 3 feet is 12 foot ounces. Notice here this transfer function actually has a unit of measure. Kind of wild, isn't it? When there are different units of measure, that gets put in a transfer function or a gain function. When you have things like get so many volts per milliamp, that's volts per milliamp. You get so much current per volts, milliamps per volt. You have so much of an opening in a valve, and you signal by 4 milliamp, well, I'll take IP converters. You go from milliamps current to PSI in air. So your transfer function is PSI per milliamp. And that's for your transfer function. What's your unit of measure for your input? What's your unit of measure for the output? And here what's pretty tricky is that it's the whole thing here. It's foot-pounds per pound, but pounds divide out, so it winds up going to feet. So I'm transferring a transfer function from input force to an output torque. It's in length, it's a unit of length. Now if I had feet, like I could adjust a lever, you get so much torque, then it's going to be in terms of pounds. So you get foot-pounds per foot. Now, there wasn't a whole lot of math really involved in number crunching as far as coming unit of measure. It's really drawing it out and saying, okay, what's my input, what's my output? And output up top, numerator, input in the denominator. And that gives me the unit of measure for that transfer function. Now, in all numbers, when you do math, data recording, whatever you do, when you write down data, presumably for either yourself to review some other time later, or some other person to review, could be technicians, managers, engineers, whatever. Never know who's gonna look at this stuff, but sometimes you look at old quality records. What does this machine do for the last 5 years? Just look for 5 years of quality records and see if they can see a gradual decline or sharp declines in place. Unit measure is important to figure out what to look at. You know, the unit measure should be correct. This should be a habit, always report unit. I want to say on test equipment, report what you see. So if I set my multimeter to read kiloohms, I'm reading resistance and I get 0.35 kiloohms, I'm putting 0.35 kiloohms. I might put 350 ohms if I'm translating to ohms, and trailing zero goes in there. But let's say if I see a trailing zero, I usually put the trailing zero down. It doesn't imply on a meter the accuracy of it. I know sometimes people like to round 0.379 to 0.4. If you're doing current calculations for NEC, yeah, that's fine. If you're reporting as a data point for something like a current loop, I'd want to see all the digits. So we have the force of habit for recording data. I generally just put down what I see, including the trailing zeros and that sort of stuff, and just record in there. I can always ignore it later. As a matter of context, what I'm doing with. As I said, again, if what I'm looking for is like a voltage applied across the motor, that's close to nominal. Whole numbers are fine. I'm adding up currents for sizing a circuit breaker and overload. Realistically, whole amps are fine in total, but that's acceptable. If we're doing things like signals, I tend to go a lot deeper in there. I'm going to stop here, pick this back up Monday, and start to work with some actual numbers. Hopefully you got out of this a little bit about where proportional band is going to sit. Proportional gain ultimately is going to be this transfer function, and the concept of input and output ranges, and how that defines what we want, what we're trying to achieve. And hopefully see you all Monday. Monday. Sorry to keep track of holidays. I don't think I have another one until